So in the last couple of talks, we've discussed the exponential function e to the x, which looks like most exponential functions, and the logarithmic function, the natural log of x, which we said is log base e to the x, we found. And now that we found derivatives and antiderivatives for them, how about if we go to different exponential and logarithmic functions? So that's the goal of today, is to try to come up with things for log base a of x and a to the x. So in order to do that, we're going to start out with looking for a relationship between a to the x and e to the x. So I can say that a to the x is e to the natural log of a to the x. Because e to the natural log of anything is just that number, because e to the x and natural log of x are inverse functions. Well, then I can take this x up here and bring it in front of the natural log. And there I've got it. I'll rewrite it over here. A to the x equals e to the x times the natural log of a. So it's very close to e to the x. It's sort of like having e to the 2x or e to the 5x. It's just whatever the natural log of a happens to be, that's a number. So it's going to look very much like e to the x. It's just going to have a slightly steeper or less steep slope. Well, once we've done that, can we find out a derivative? What's the derivative of a to the x? Well, if we're going to look for the derivative of a to the x, we should look for the derivative of e to the x times the natural log of a, because we already know how to do that. Well, the derivative of e to something we found out was just e to whatever that is. And if it's anything other than x, we have to do the chain rule and multiply by the derivative of this other function. Well, it's not a really complicated function, but it's not just x. So what's the derivative of a constant times x? It's just that constant. And then e to the x natural log of a is just a to the x. So we got it. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x, just times the natural log of a. So there's a new formula. We just have this extra constant. Okay, how about the antiderivative of a to the x dx? Well, we can do the same thing. We can make it e to the x natural log of a, because we already know how to take antiderivatives. But since this is not just x up here, we have to do a u substitution. So if we let u equals x natural log of a, then du is the natural log of a times dx. Because again, that's just a constant. So if I rewrite this, I get e to the u, and what is dx? Dx, if you solve for it, is 1 over the natural log of a times du. Dx equals 1 over the natural log of a times du. So I get this 1 over the natural log of a, and the antiderivative of e to the u is e to the u. And then if you just put the u back in there, I get e to the x natural log of a, and e to the x natural log of a is just a to the x. So the answer is just a to the x, but then times this 1 over the natural log of a. So the antiderivative of a to the x is a to the x times 1 over the natural log of a. And probably, if we're really going to put this into one of our new forms, it would probably best to put, instead of x, to put u. But, so if you put a to the u times du, it would be a to the u times 1 over the natural log of a. Well, how about this log base a? We know from back in algebra that log base a of x and a to the x undo each other. They're inverse functions. So the question is, what is the relationship between log base a of x and a to the x as far as how do they relate to e, log base e and e to the x? So we're looking for an inverse function of a to the x. Well, that is e to the x ln of a. So if I were to take the natural log of e to the x ln of a, I would just get x ln of a, because the natural log and e to the x are inverse functions. So the natural log doesn't quite, it isn't quite the inverse of a to the x. But if I were to take a 1 over the natural log of a and put it out in front of here, so if I consider this the function, then I would have this times 1 over the natural log of a, I'd get right back to x. So it looks like the inverse of this, which is really a to the x, the inverse function is this function, 1 over the natural log of a times the natural log. And we know that this is the inverse of a to the x, which means that this must equal this. So now we see the relationship between log base a of x and natural log of x. They're the same thing except for this extra constant that comes out in front. So again, log base a of x would look much like this. It's just every y value would be multiplied by whatever this constant is. And the thing that makes that so important is now we can find out what the derivative of log base a of x. The derivative of log base a of x is really just the derivative of this. So we just take that constant times the derivative of the natural log of x, which is 1 over x. So we also have a formula here. 1 over the natural log of a times 1 over x. So you can see all of these formulas are very similar. They just have these extra constants that get multiplied by them. So we're almost ready to do a few examples. But why did I put this down? This is something we've had the power rule along for a long time. We said the derivative of this was nx to the n minus 1. It's probably the derivative formula we've used most often. Well, the thing about it is back when I did that, in lesson number, around 10 or 11, we used the binomial theorem to prove that. So it only really has been proven for values of n that are positive integers. So I'm thinking this is the time that maybe I can make up for that and show you that it works for all real numbers. So if we take x to the n, we can write that e to the natural log of x to the n. For the same reason we did it over here. E to the natural log of anything is just going to be that number because they're inverse functions. So if I want to take the derivative with respect to x of x to the n, I can just take the derivative of this. And the first thing you would probably do is take that n and put it out front there. So what's the derivative of e to something? It's e to whatever that function is. Then we have to finish the chain rule and multiply times the derivative of that function. So what's the derivative of that? It's this constant times 1 over x. And then I can take this n and put it back up here. So I can put that back up here. And what do I get? E to the natural log of x to the n is just x to the n. Then you have to multiply it by n and then divide it by x. So what do you get? N x to the n minus 1. And I did not use any type of theorems that are only good for integer values. This works for all real numbers. So now you can feel good about using this for fractions and negative numbers. Okay, so let's use some of these new formulas to do a few problems over here. Now, we're starting out right here with y equals x to the pi. Well, not only can you use this formula that we just proved for negative numbers and fractions, you can also even use it for irrational numbers like pi. So the answer is, we can use the power rule. Pi x to the pi minus 1. We're done. That's dy dx, or y prime of x. Number 2. We have log base 3 of x squared plus 1 as our function. We want to find the derivative, the slope, the instantaneous rate of change, all those things that mean the same thing. We want to find it at x equals 1. So f prime of x. So because it's log base 3, we have that extra pesky constant that we have to just kind of memorize from the formula. Then it works just like the natural log. So the derivative of the natural log of x is 1 over x. But we have to do the chain rule because this is not x, it's a function of x. So we go 1 over x squared plus 1, and then times the derivative of that, which is 2x. So that means f prime of 1 is going to be 2 divided by 2, or 1 over the natural log of 3. And that's our answer. That's a slope. That's a number. 1 over the natural log of 3. You put it into your calculator, you can find out exactly what number that is. Okay, now we have an exponential function. Y equals 2, not 2 to the x, but 2 to the x cubed. So you can see already, because that's not just x, we're going to have to do the chain rule again. That's a really important formula, isn't it? A rule. So what is dy dx, or y prime of x? It's 2 to the x cubed, but then we have to multiply by the derivative of x cubed, which is 3x squared. In other words, if that was e to something, the derivative would be e to something. If it's 2 to a function, the derivative is 2 to the function, but then we have to finish the chain rule and multiply by the derivative of this other function. And then that extra pesky constant has to come along. Now we're trying to find a tangent line at x equals 1. So we have to plug into the derivative 1. And we get 2 to the 1 times 3 times 1, so 6 times the natural log of 2. And that's just a number. That's the slope. What's the point? Well, we have x is 1, and what's y? Y is 2 to the 1. So we've got a point. Now we can write the tangent line. Y minus 2 equals that number times x minus 1. And that would be the equation of our tangent line. Okay, now we've got a definite integral. And we have to look for any new forms that we've learned. Well, we did learn a new form. The integral of a to the u du was a to the u times 1 over the natural log of a plus c. So we're going to have to try to get it in that form. It's not just 4 to the x. So what we're going to do is a u substitution. We're going to let u equals the cosine of x. So du is minus the sine of x dx. And I have to rewrite everything. So this becomes, I'll just circle it as I replace it, that's going to become 4 to the u. And then I have to look at what's sine of x dx. From here I can see sine of x dx is just minus du. And then 0 becomes the cosine of 0, which is 1, and pi over 2, the cosine of pi over 2 is 0. So we've transformed the original one into a new form that we know, a to the u du. And if you don't like to go from big numbers to small numbers, we're always allowed to take that minus sign and go from 0 to 1. So what's the antiderivative? The antiderivative of 4 to the u is 4 to the u. It just has this new pesky constant, 1 over the natural log of 4. And then I go from 0 to 1. So I get 1 over the natural log of 4 times 4 to the first power, 4, minus 4 to the 0 power 1, I get 3. So 3 over the natural log of 4. Again, that's just a number. That's the answer to that definite integral. Well, let's try another definite integral. These are a little bit tougher, so I thought we should do 2 of these. Again, if you look at this, you see a number to a function. I wonder if this one is also in the form of a to the u du. In order to do that, I'm going to have to let u equals 2 over x. Or 2x to the negative 1 if you like that better. So what is du? Du is minus 2x to the negative 2 times dx. So let's just see if it works. If I circle that, I can replace that with 5 to the u. I could take this 2 and just put it right out front as 1/2, then I don't have to deal with it. And what do I have left? I have left x squared, or dx over x squared. Well, there is right there dx over x squared. So if I want to solve for that, I multiply both sides by negative 1/2, and I get dx over x squared is negative 1/2 du. So I can just multiply by another negative 1/2 out here, and then just put du. And 1/2 right here becomes 2 divided by 1/2, or 4, and then 1 becomes 2 divided by 1, or 2. And you can do it just like that, or like the last problem, instead of making this negative 1/4, I can make it positive 1/4, and then go the other way on my definite integral. So, what's the antiderivative? We already have the 1/4 here. We're going to have this new constant, 1 over the natural log of 5. And then we just get 5 to the u. It's 5 to the u times 1 over the natural log of 5 from 2 to 4. So we get 1/4 times 1 over the natural log of 5, and then 5 to the 4th is 625 minus 5 squared, which is 25. So you get 600 divided by 4, or 150 over the natural log of 5. And that would be the answer to that definite integral. Okay, so let's end with a couple of word problems. And this, again, is reviewing some of the things we've done earlier in the year. So, a captain derivative rookie card, I don't know if anybody has any of those, but they're worth, right now, $8,000. And it's projected that their value is going to be that many dollars over the next several years, where t equals 0 is now, and t is measured in years. How fast will the card be increasing in value in 4 years? So what do we have to think? We're not looking for the value of the card, we're looking for how fast it's increasing. So we want its derivative, its rate of change. So we want v prime of t. So we're going to have to take the derivative, and then it's at 4 years from now. So if t equals 0 is now, t equals 1 would be 1 year from now, so t equals 4 is 4 years from now. So in my mind, I know what I have to find is v prime of 4, and I'll have the answer. So what is v prime of t? It's 8,000, that's just a number. And the derivative of 3 to the x is 3 to the x times the natural log of 3, but that's not x, and in fact, it's not t. It's the square root of t. So we have to do the chain rule again. So we go 3 to the square root of t times the derivative of the square root of t. Well, that's 1/2 t to the negative 1/2. And then you still have that extra constant that comes in the new formula. So that should be the answer. So if we want to know v prime of 4, it's going to be 8,000 times 3 to the square root of 4, so 9, times 1 over 2 times the square root of 4, so 1/4 times the natural log of 3. So 2,000 times 9 is 18,000 times the natural log of 3. And what would the units be in? This is a derivative, so they'd be in dollars per year. So not only could you find out how much it's worth in 4 years by plugging it into here, you could find out how fast it's going to be increasing at that time, and whether it's a good idea to hang on to it. I'd hang on to it if I were you. Okay, so we're going to end up here with a circle. And that circle is changing as a function of time. So at time t, this is the radius of the circle. And we want to know how fast the area of the circle is increasing at time pi seconds. So what we want to find is dA dt, the rate of change of the area with respect to time. We don't have any rates, but we can get the rate of change of the radius. And the radius is related to the area. So this is a related rate problem, which we used to do quite a few of those, but we haven't done any in a while. So what is dr dt? Well, pi is just like it is a number. It's an irrational number, but it's just like having 5 to a power. So we're still going to use that new derivative. So the derivative is going to be pi to the t over pi, but then we have to do the chain rule and multiply by the derivative of t over pi, which is that's just 1 over pi times t. So the derivative is going to be 1 over pi, and then we have that constant that becomes a part of the formula times the natural log of pi. So there's our formula, and we want to know what dr dt is at t equals pi. So dr dt at t equals pi is going to be pi to the pi divided by pi, which is 1, times 1 over pi times the natural log of pi. And these just cancel out. So we now know what dr dt is. So what's the relationship between A and R? A equals pi r squared. So dA dt, what we're looking for is 2 pi r times dr dt. So dA dt, when t equals pi, all I have to do is plug it in. I get 2 pi times r, and what's r? R is, from up here, r is going to be pi to the pi over pi. So that's pi. And what did we find out dr dt was? That was the natural log of pi. So altogether, the answer is 2 pi squared times the natural log of pi. And we should have units because this is a word problem. So dA dt would be in, let's see, r is in centimeters, so it would be in square centimeters per second. So that would be how fast the area would be increasing. We already know how fast the radius is increasing. So, some good review problems. We've got a couple new formulas. I think that's probably enough for a day. So, take care.